protecting employees unnecessarily. You don't want to have too much equipment on that could get in your way if you don't need to have it on to be protected. Okay, now the arc flash calculation, this is from the NFPA 70E table. It's developed by Ralph Lee, a DuPont consultant in 1982. This method assumes arc current is equal to the voltage fault current. This is okay for systems over 600 volts, but can lead to incorrect PPE sizing. A 1000 kVA transformer with a secondary voltage of 480 has a 6% impedance using the Lee method. We assume 20 kA of voltage fault current is available. This is assuming an infinite bus. This results in a clearing time of 0.11 seconds or 4.4 calories per centimeter squared at 18 inches. If we consider the system's impedance, available fault current is actually closer to 10 kA. It takes our OCPD 2.5 seconds to clear and unleashing a 53.2 calories per centimeter squared at the same distance. Because specific fault currents and clearing times are not used, improper PPE can result, as you can see from those two examples. The first thing you always want to do before you go to work on any live equipment is to make it not live and lock out and tag out that equipment. When we go through what the difference is between electrical lockout tagout and normal lockout tagout are. Okay, an unqualified person are classified as affected persons for electrical lockout tagout. Electrical lockout tagout requires all the same steps as normal lockout tagout, plus it requires a voltage test. Because only qualified workers can approach exposed energized parts close enough to take a volt reading, only qualified workers can perform electrical lockout tagout. A person who is unqualified to perform electrical work may still be qualified to shut off the electrical devices for non-electrical lockout tagout procedures. And this is basically stating that an unqualified employee may go to shut off and lock out and tag out a device if he's working on non-electrical lockout procedures. Okay, this means that an unqualified worker is able to operate a circuit breaker as part of the lockout procedure without violating any regulation because there is no exposed electrical parts. When the breaker is safely positioned and a covered electrical panel must be covered for him to be able to do this. Therefore, an unqualified worker is then able to lock out a breaker that he or she must operate in order to safely service a machine, provided that he or she will not have to touch any normally energized parts during that job. The job requires that normally energized parts will need to be exposed, and this is considered electrical lockout, and a voltage test is required to verify the normally energized parts so that they can, or to verify that they're at the zero energy state. Okay, here's an example situation. If a worker intends to service a drive system on a pump driven by an electrical motor, he or she must lock out and tag out the electrical breaker that feeds the motor before placing their hands in the drive system. This is considered normal lockout, and the generic 1910.147 OSHA procedures apply. In this case, a worker who is considered unqualified for electrical work may safely operate a circuit breaker because the panel presents no electrical hazards to the worker. However, if the worker intends to change out that same motor and expose the normally energized motor leads, then this is considered electrical lockout. Because this job involves exposed electrical parts, only a qualified electrical worker can perform the job. Obviously, if any work requires a worker to expose normally energized parts, that job must be performed by a qualified electrical worker. Here are some unqualified worker limitations. Okay, approved work activities. Routine operation of a circuit breaker, such as non-electrical lockout tagout. He can approach or use electrical equipment that has no energized exposed parts. And he can assist qualified workers on equipment that has been properly locked out and tagged out. Okay, now prohibited work activities is that he cannot reset circuit breakers following a trip, taking voltmeter readings, pulling fuses, approaching closer than 3.5 feet to the exposed electrical parts. This is shown by the ranges that I've gone over earlier. So as you can see, the unqualified worker can still do a lot to get to work on non-electrical equipment, but needs a qualified worker to be able to do anything other than that. A qualified worker must be there to do all of the rest of them, the taking voltmeter readings and pulling fuses. Okay, exposed electrical equipment means that there isn't something between you and the energized parts. So, as you can see in the top picture there, that is a completely closed MCC and there's no energized parts that are exposed that you could accidentally touch. But in the bottom picture, with that door open, that is now an exposed energized part. Unqualified workers must stay well clear of any exposed electrical equipment. All right, I'm going to go through our arc flash assessment now. This is step one. The first thing we're going to do an arc flash assessment is to verify plant single lines. Okay, to do this, we need the utility info, the transformer data, the OCPD types and settings, cable types and lengths, and large motor and generator information. That includes anything over and including 50 horsepower. If the single lines are not good, sometimes it's a good idea to go and get those corrected before starting an arc flash assessment. The second step is short circuit analysis. This determines the magnitude of available fault current throughout the power system at various time intervals following a fault. The computer model is used to determine the voltage three-phase short circuit current. Once the fault levels have been calculated, they are compared to the withstand rating of the equipment in the electrical distribution system. If the breaker is rated at 80,000 amps, asymmetrical, 50,000 amps symmetrical, it can withstand at a first 1/2 cycle of 80,000 amps and a fall of 50,000 amps. If the equipment is underrated, it can fail to operate properly and cause an even greater hazard than if it did not operate at all. Okay, step 3 is protective device coordination study. A coordinated system is one in which the protective devices, circuit breakers, fuses, relays, any other OCPDs, operate at the proper times to eliminate or minimize the damage to a system. In the worst case, no protective devices will operate, resulting in risk to both the equipment and the personnel. Changes in loading or equipment required revisiting this analysis every few years. So basically, you want to go in for a protective device coordination analysis, and you want to operate from a ground up way. You want to start with your motors or your lowest protective device on that motor and work your way back to the utility. The OCPDs should operate from there up if an arc flash happens. This one should go first, and as you get higher, then they should trip to cause less of an arc flash. In general, coordination studies are conducted from a bottom-up fashion, according to the general guidelines identified below. Like I said, we're going to start with individual loads, then we're going to go conductors to loads, distribution equipment such as breakers and disconnect switches, and then transformers, and then eliminate or minimize the damage to a system. In the worst case, no protective devices will operate, resulting in risk to both the equipment and the personnel. Changes in loading or equipment required revisiting this analysis every few years. So basically, you want to go in for a protective device coordination analysis, and you want to operate from a ground up way. You want to start with your motors or your lowest protective device on that motor and work your way back to the utility. The OCPDs should operate from there up if an arc flash happens. This one should go first, and as you get higher, then they should trip to cause less of an arc flash. In general, coordination studies are conducted from a bottom-up fashion, according to the general guidelines identified below. Like I said, we're going to start with individual loads, then we're going to go conductors to loads, distribution equipment such as breakers and disconnect switches, and then transformers, and then your high voltage distribution to the transformers. Okay, the above process is continued for every voltage level until the utility control devices are reached. After we get all the short circuit and protected device information, we go to step 4, which is an arc flash hazard analysis. This determines the incident energy at each point in the power system based on the previous information. These energy levels are only as accurate as the information gathered through the first 3 steps. I don't know if you can see this below here, but this just results in arc flash calculations from 23 kilovolts down to 4160 volts, and then 480 volts lastly. It's going to show you everything from your kilovolt bus all the way down to your incident energy. It's going to show you your working distances and your clearing times as well for your protective devices. In this particular study right here, the 4160 volt system or bus is the most dangerous, even though it's not the highest voltage. A lot of times this is the case with 4160 volts. Here are your PPE requirements. This is listing for the different hazard and risk category numbers. Now, note 4 on the right, regular weight cotton or denim cotton jeans are acceptable in lieu of FR flame resistant pants. The flame resistant pants used for the hazard risk category 1 should have a minimum ATPV of 5. This is just showing you what you will need for different categories from 0 to 4 for your protective or for your PPE requirements. I'm going to go over this a little more in a second. Okay. Now when you get into using the clear UV face shield, it has to be rated at 1.2 calories per centimeter squared. After that, you want to use a gold reflective UV face shield of 7.33 calories per centimeter squared. Okay, the 24 per 30 ounce FR coverall switching unit is used for 40 calories per centimeter squared. This is a full flash suit. But this also includes an arc hood. This is for 45 to 75 calories per centimeter squared. Now I bet you're all wondering what calories per centimeter squared are in which categories. Now the categories go from 0 to 5, 5 being dangerous and unworkable. You cannot work on that equipment live at all. So your 0 category is from 0 to 2 calories per centimeter squared. This is just untreated cotton, leather gloves, safety glasses, your basic PPE in a steel mill or anywhere like that. Now, your 1, you're getting into 2 to 4 calories per centimeter squared. Not a big jump yet, but you still want to be wearing rubber gloves when you're working on this and a hard hat. Also, you want to make sure that you're wearing a flame-resistant shirt and pants, like I said before, or jeans. When you get to category 2, you got 4 to 8 calories per centimeter squared. This is including all of the previous and adding on to an arc face shield, which can be attached to your hard hat and will protect you from any, protect your face from any explosions or flashes. Now 3 is where a big jump occurs and you get from 8 to 25 calories per centimeter squared. This is going to be having everything before, except for now we're going to add in an arc hood and an arc jacket over top of your shirts and pants. Category 3 can be very dangerous when you get up into the 20 ranges. You definitely want to be protected over your whole body and not have anything showing, because any exposed skin in this area will definitely incur third-degree burns or worse. And category 4 being the worst that you can actually work on live is 25 to 40 calories per centimeter squared. You're going to be wearing all the stuff you were wearing before, starting with your FR shirt and pants, rubber gloves, safety glasses, hard hat, arc hood, but you're also going to be wearing a multi-layer flash suit. Okay, this suit is going to protect you for up to 40 calories per centimeter squared, and anything over that, this suit is not even good enough. So when you get over that 40 calories per centimeter squared, it's dangerous and you cannot work on it. That's our presentation for how we go into the form and some information on an arc flash hazard and analysis. Thank you.